Hi everyone, let's look at the Gabriel synthesis of a primary amine. Okay, what's happening here? So if you have an alkyl halide and from the Gabriel synthesis, we should be able to get a primary amine. And this reaction works with phthalimide. So this is the phthalimide. You can see it's a amide group, NH, but you have two carbonyl groups. This reaction works in the presence of a base, hydroxide. It's going to go and take the hydrogen on the nitrogen. Now, once the hydrogen is lost, nitrogen can act as a better base, more stronger base. Now, this nitrogen goes and react with the alkyl halide in SN2 fashion. Okay, so the alkyl group will add on to the nitrogen and then the bromide will be lost. Then once that is happened, you heat it in the presence of acid, hydrochloric acid and water. So then the amide group is going to hydrolyze. Okay, from this side you're going to get the carboxylic acid, from this side also you're going to get the carboxylic acid, and from the other side the nitrogen will become a protonated primary alkyl ammonium ion. Okay, hydrogen will be on this nitrogen. And then when you add a base, so the alkyl, the protonated ammonium ion will become primary amine, and this will also become deprotonated. So the synthesis requires hydrolyzing two amide groups. So the two amide groups. Okay, so the Gabriel synthesis will give you a primary amine with alkyl halide. Okay, a nitrile. So what is a nitrile functional group? So carbon with the nitrogen with triple bonds, 1, 2, 3. Cyano group is called a nitrile. And this one is called acetonitrile with the CH3 group. Let's look at how to name these nitriles. Systematic name, ethane nitrile. There are two carbons. So meth for one carbon, eth for two carbons. So ethane nitrile or acetonitrile, methyl cyanide. So they are the names. And this is benzene carbonitrile or benzonitrile phenyl cyanide in other words. And this one, let's see how the systematic name. One, okay. How many carbons? 1, 2, 3, 4, 5. Okay, 6. 1, 2, 3, 4. Yeah, that's what I was looking for. Right. 1, 2, 3, 4, 5. On the fifth carbon, you have a methyl group. So 5-methyl hexane nitrile. 5-methyl hexane nitrile. Okay. Delta methyl capronitrile, don't worry about that. Isohexyl cyanide, don't worry about it either. Just know how to name it systematically. 5-methyl hexane nitrile. And then this one, 1, 2, 3 carbons, propane nitrile. Propene, because there's a double bond right there. Propene nitrile or acrylonitrile. Acid catalyzed hydrolysis of a nitrile. So when you hydrolyze a nitrile, it gives you carboxylic acid. Nitriles are harder to hydrolyze than amides. Here's the mechanism how a nitrile hydrolyzes to give you a carboxylic acid. So nitrogen has 3 bonds and also it carries its lone pair that can act as a base. It's going to go and grab a hydrogen from the acid. So it will have a protonated nitrogen just like the carbon, a carbonyl group, protonated oxygen. When you have a carbonyl group protonated, carbon is more susceptible to nucleophilic attack. So similarly, once the nitrile group nitrogen is protonated, now the carbon is more susceptible to nucleophilic attack even by a neutral molecule. So the water attacks the carbon. So one of the pi bonds, out of the 2 pi bonds, 1 pi bond breaks. So you have this intermediate carbon nitrogen double bond nitrogen hydrogen. Okay, and then the water molecule has now its 2 hydrogen bonds. The base will grab 1 hydrogen and it forms this intermediate right there. After oxygen lose a proton. Okay, now again what's going to happen is nitrogen, just like it did at the first time with the nitrile group, now you have a carbon nitrogen double bond. Nitrogen again gains another proton, a second proton is gained. Okay, now again the nitrogen will become positively charged, and what happened now is instead of another water molecule attacks, this OH, okay, gonna form a pi bond, and then the carbon nitrogen pi bond breaks. Now this is a resonance structure with this one. Resonance contributors for a protonated amide. Okay. Okay. So this one, and then you add water again to this molecule one more time, just like same earlier. Water molecule adds on to the carbon, and similarly another water molecule can add on to this carbon. Okay, and then either one is fine, but this nitrogen will again gain a proton and become ammonia, and then after several steps ammonia can be lost and then it forms the carboxylic acid. Okay, that is the mechanism how a nitrile forms a carboxylic acid. Synthesis of a carboxylic acid from a alkyl halide. Alkyl halide, a cyano group, a nucleophile in SN2 reaction, leaves bromide, cyano group is added. Now we have a nitrile. We do this reaction in DMF. DMF stand for dimethylformamide. Okay. Nitrile, when you heat the nitrile in the presence of acid, so it gives you carboxylic acid. So by this reaction, alkyl halide with 2 carbons can form carboxylic acid with 3 carbons, 1, 2, 3. We can synthesize a primary amine using a nitrile. Using hydrogen and Raney nickel will reduce the carbon-nitrogen triple bond to RCH2NH2. It's a primary amine. Another category of carboxylic acid derivatives is acid anhydride. Okay. In acid anhydride, you can see this is oxygen, and then you have 2 carbonyl groups next to the oxygen, and then you can have some alkyl groups. So we call that as acid anhydride, and this is acetic anhydride. How do we form acetic or any anhydride? It is formed when water is lost from 2 molecules of carboxylic acids. So these are carboxylic acids. You condense them, you heat it up, you use a water molecule, and then you can form the acid anhydride. Nomenclature of acid anhydrides. This is called ethanoic anhydride because there are 2 carbons, symmetrical. Ethanoic anhydride or acetic anhydride is the common name, which is a symmetrical anhydride. And this one is, it has a carbonyl group with 1 carbon, and this has 2 groups, 1, 2. So this is ethanoic methanoic anhydride. Ethanoic come from this side with the 2 carbons, methanoic come from this carbon with 1 carbon. Ethanoic methanoic, and it goes by the alphabetical order at ethanoic methanoic anhydride or acetic formic anhydride. Acid anhydrides are less reactive than acyl chlorides but more reactive than esters. Most reactive going to be acyl chlorides, and esters are going to be more reactive than acyl chlorides, and acid anhydride stays between these two. Some of the reactions of acid anhydrides: in the presence of an alcohol, you lose this part, and in the carbonyl group, carbon adds on to the oxygen of the alcohol. So you can form an ester and carboxylic acid. And if you have the same R groups on each side, when you add water, you can get 2 carboxylic acids. And with methylamine, this group is replaced with the amine group. And then from this side, you generate carboxylate anion. Acid anhydride, like an acyl chloride, requires 2 equivalents of an amine. Here's the mechanism how the acid anhydride react with an alcohol to give you a carboxylic acid. It's a symmetrical anhydride, so the alcohol can add on to any of the carbon-al-carbon. Okay. Again, the pi bond opens up, so we have the alcohol part here. Base takes up the hydrogen, become neutral again, and then so the negative charge on the oxygen helps to reform the carbonyl-carbon, and then it breaks the carbon-oxygen bond. Okay, so it forms the ester. Now you have R, C, double bonded oxygen, OR group, which is the ester. And from this side you have the carboxylate ion. When you add an base, conjugate base, it will grab a proton and then it can become carboxylic acid. So it's making ester and carboxylic acid by reacting with an alcohol. Excuse me. Excuse me. Here you can see some analgesics. So the first one is morphine, most widely used analgesic for severe pain, and it is a standard by which other pain-killing and medications are measured. Okay. Most commercial morphine is obtained from opium, which is a milky fluid exuded by a species of poppy. Okay. Morphine occurs in opium at very high concentration, as high as about 10%. Opium was first used for its analgesic properties maybe around 4000 BC in Roman times. But what is the difference between morphine and the codeine? So you see here there is a OH group over there. When this hydrogen is replaced by a methyl group, you get the codeine, which is a less effective painkiller than morphine. It's about 1/10 of the strength as the morphine. So it helps to suppress cough, right? It inhibits the cough reflex. And then what about the heroin? Excuse me. Which is even more potent, which is much potent and more widely abused than morphine. It is also synthesized. How it is being synthesized? It is synthesized by acylating the OH groups. You see here, 2 OH groups on morphine. Now you have acylated group over there. So when you treat morphine with acetic anhydride, you can form heroin. Since it uses acetic anhydride and puts acetyl group on the OH, acetic acid also formed as a byproduct when the heroin is being synthesized. So normally to detect the heroin, drug enforcement agencies, they use dog's brain to recognize the pungent odor of the acetic acid. Okay, so the dogs are detecting acetic acid by way of detecting heroin. Excuse me. Dicarboxylic acids, meaning when you have two carboxylic acid in the same molecule. So this is oxalic acid, malonic acid, succinic acid, glutaric acid, adipic acid, phthalic acid. So these are common names of these acids, and also given pKa1 and pKa2 of the two acidic hydrogens. So you can see the first one is more acidic, but the second hydrogen is less acidic compared to the first one. The two pK values are different. For this one, acetic, what is this one called? Malonic acid. Yeah, malonic acid. pKa1, the first hydrogen is more acidic, 2.86. And then the pKa2, the second hydrogen, is 5.70. Why? The neighboring two carboxylic groups withdraws electrons and lowers the first pKa. And then the electrostatic repulsion between the like charges raises the second pKa. So when you have dicarboxylic acid like this, they can lose a water molecule when heated if they can form a 5 or 6 membered ring. So it can rearrange. So this is the glutaric acid, lose a water molecule, okay, and one oxygen will be left and form glutaric anhydride, a cyclic anhydride. 5 or 6 membered ring. So this is a 6 membered ring. And phthalic acid, when you heat it, it can form a 5 membered ring, that is phthalic anhydride. So this anhydride formation can be catalyzed by acetic anhydride or acetyl chloride. Succinic acid with the acetic anhydride, you can form succinic anhydride. And also it generates two acetic acids. Activating carboxylic acids by converting them to acyl chlorides. Normally we learn that acyl chlorides are more active than carboxylic acids. So if you want to do a reaction with a carboxylic acid, what normally do is convert it to a acyl chloride first. Now this is carboxylate anion. React with thionyl chloride, so that will give you acyl chloride. So these are going to be more reactive now. Okay, so the reagents we use thionyl chloride or phosphorus trichloride to convert to acyl chlorides. These reagents give the carboxylic acid a better leaving group than chloride ion. Now even better way to do that is converting better leaving group than chloride ion with these reagents. Chlorine ion is not the group that is eliminated. Chloride ion is not the group that is eliminated. So we can convert the carboxylate anion to these groups. Thionyl chloride and PCl3 phosphorus trichloride. It forms these intermediates, forming good leaving groups. Wait, it's only a few more left. Okay, so let's go ahead and finish this up here. Okay, so once you form these intermediates, the chloride ion react with the carbonyl carbon. You know the process now. Carbon-oxygen bond opens up, reform the carbonyl group and leave this group. And in here you are making sulfur dioxide and chloride ion. Sulfur dioxide again is a small stable gaseous molecule that would make the reaction go forward much more readily. Okay, and from the acyl group, a better leaving group than a chloride ion. So we can form acyl chloride from carboxylic acid. Once you convert a carboxylic acid to a acyl chloride, it can undergo a wide variety of reactions, and it can also produce different carboxylic acid derivatives. So acyl chloride with carboxylate anion, you can form anhydride. With alcohol, you can form an ester. With amine, you can form an amide group. We call this process as activating carboxylic acids by converting them to acid anhydrides. So in the presence of phosphorus diphosphorus pentoxide, carboxylic acid can form anhydrides. Okay. So this concludes our chapter 15, which is the carboxylic acids and carboxylic acid derivatives. It's a lot of information, but you got a lot of knowledge. Okay, then we'll stop over here.